Welcome to Online Precalculus. This is section 2.1, Complex Numbers. In this section, we'll talk a little bit, we'll start talking with the imaginary unit I and how that relates to square roots of negative numbers and how we can evaluate I for all different exponents. Then we'll add and subtract complex numbers, multiply, divide complex numbers, perform operations with square roots of negative numbers, and finally solve quadratic equations with complex imaginary solutions. So any any discussion about complex numbers has to start with the imaginary unit I, okay? And the imaginary unit I is defined as something that has a square root of -1. And if we think about square roots, what they mean, right? If I want to find the square root of 16, I'm asking myself what two numbers multiply together to give me 16, 4 and 4. But what two numbers multiply together to give you -1? Remember, they have to be the same. And there are no real numbers that multiply together to give you -1. So therefore, the square root of -1 is not a real number, which is why we use this imaginary number, I, a number that's not real. It's imaginary. By definition, I is equal to the square root of -1. And therefore, if we were to square both sides here, right, I squared, the square root and the square root just cancel out. I squared would be -1. Okay, so using the imaginary unit, we can now express square roots of negative numbers as some multiple of I. So in this example right here, we have the square root of -25, right? We can't do that with real numbers, but now we can because we can split that square root into -1 times 25, square root of -1 times square root of 25. By definition, the square root of -1 is I, and so this becomes, I could take the square root of 25, that's just 5. So it becomes 5I. And you can check this by squaring 5I, and by definition, I squared is -1, and we do get -25. So a new system of numbers called complex numbers is based on this imaginary unit I and putting it together with real numbers. Okay? So a complex number is in the form A plus BI. Every number is a complex number. Okay, we're expanding our definition of types of numbers, classifications of numbers. Before, we just really had a classification for real numbers, right? Real numbers could be rational or irrational, and rational numbers could have been natural, whole, integers, all those different types of classifications. Now we're expanding that definition with complex numbers. Complex numbers can have two parts. It can be real or imaginary. Okay, this A is the real part. The BI is the imaginary part. Okay, so if a complex any number is a complex number. Okay, a real number has B equal to 0, right? There are no imaginary part, and imaginary numbers have both parts. And then if it's just the imaginary part, if it's just BI, then that's called a pure imaginary number. So if we look at a couple examples here, okay, these are some examples of complex numbers. That is a complex number. It is also an imaginary number. This is a complex number. It's also a pure imaginary number. So really, imaginary numbers just have two classifications, imaginary number or pure imaginary number. Okay, one is the subset of the other one. This is a complex number. 3 is a complex number. It has no imaginary part, therefore it's real. And underneath real numbers, we can say that it's actually a natural number. But the classification of complex numbers now applies to any type of number, and the imaginary numbers that we're going to be working with are going to be ones that have an I in them. To simplify it, right, a complex number is said to be simplified if it's expressed in the standard form of A plus BI. Okay, whenever we are simplifying any complex number, we're always going to put the real part first and then the imaginary part. If it has a radical, if b has a radical, we write I before the radical, like that. If you just compare these two, right, you can see that this one, the I is kind of outside the radical. This one, it's inside, but it can be very hard to tell, especially if you're writing and not reading it from some typing. Okay, so we always write the I before the radical just like we do variables, just to help us be clear about whether the I is part of the radical or not. If they are expressed in complex form, or in standard form, complex numbers are equal if and only if the real parts are equal and the imaginary parts are equal, right? So 3 plus 2i is equal to 3, the real parts are equal, and 2i, right? If you mix those up, or if you put different numbers there, the two sides wouldn't be equal to each other. And I mean, that kind of makes sense, okay? It has to have a certain real part, it has to have a certain imaginary part, and they both have to be the same. Let's talk a little bit about the cyclic natures of the power of I. Okay, so whenever we're doing operations with complex numbers like we're about to do on the next page, operations on complex numbers require multiplying by I and simplifying the powers of I. So we already have that I is negative square root of negative 1 and I squared is negative 1. But we always want to simplify everything, right? We want to simplify I. Oh, we never want to have I bigger than the first power. So if I have I to the third, I can rewrite that as I squared times I, which is I squared is negative 1 times I. So we get negative I. I to the fourth is I squared times I squared, which is negative 1 times negative 1, which is positive 1. Okay. And because I to the fourth is a positive 1, that means every 4 i's that you multiply together just turns into a 1 and therefore doesn't change the value of the expression. Okay, so if we look at this and if we look at I to the fifth, right, that's I to the fourth times one more I, so that's just I again. And we can now see this pattern with the powers of I. So if the I is raised to a power that's a multiple of 4n, you're going to get 1, like I to the 512. 512 is a multiple of 4. So this is just 1. So this number doesn't matter how big it is. All you have to do is divide it by 4 and see how many i's are left over. If there's 1 left over, you get the answer to be I. If there's 2 left over, it's negative 1. If there's 3 left over, it is negative I. And again, if it's divisible by 4, it's always going to be 1. Notice that each one of these, right, my outcome for a power, something with a power of I, is only one of these 4 examples. None of those i's have a power bigger than 1. So anytime we have I to any exponent other than 1, we are always going to simplify. The most common, of course, is I squared, which is going to simplify to negative 1. That is the one we are going to see the most often. But it is good to know that we can simplify I to any power that we want. Okay? So let's do some operations with complex numbers. So a plus bi, if you think about it, is kind of like a binomial. Think about the I kind of like a variable. It's not a variable, it's a number, but think of it kind of like a variable in that when we are adding 2 binomials together, we just combine the like terms. So if you think about it like that, we can add, subtract, and multiply and divide complex numbers with the same rules that we use for binomials, with this big exception, that anytime we have an I squared, it is always going to turn into negative 1. So let's start with addition and subtraction, which are the easiest, okay? So in this paragraph, it just kind of explains that all you have to do to add and subtract complex numbers is just to combine the like terms. So you add complex numbers by adding their real part and then adding their imaginary part and expressing the sum as a complex number. and you subtract complex numbers by subtracting their real parts, subtracting their imaginary parts, and expressing the difference as a complex number. Okay, but short version is just combine the like terms. Okay, so let's try to add and subtract some complex numbers. So for adding, right, we're really not going to go too crazy here. We can, if you want to, we can drop the parentheses, right, because we don't need to have them if we have addition. So this just turns into 5 minus 11i plus 7 plus 4i. And I could rearrange them and, organize them like we did on the previous page. Or I could just say the 5 and the 7 are the real parts. They add together to give me 12. The negative 11 and the 4 are the imaginary parts. They combine together to give me negative 7i. And that's all there is to it. The trick for part B is to remember that when you are subtracting a binomial, you have to distribute the negative. Okay? So the negative gets distributed to both of those, and it turns into plus 11 plus 6i. So again, combine the real parts, negative 5 and 11, that's 6. Combine the imaginary parts, 6 plus 7i. Always write the real part first, and then the imaginary part second. Okay? Let's try 2 more with the checkpoint. Okay? Oops. There we go. So 5 and 3, that's an 8. Minus 2 plus 3, that is a plus 1i. Okay? Drop the parentheses for part B to give me 2 plus 6i minus 12 plus 1i. Okay, so that's a negative 10, 2 minus 12, plus a 7i. Okay, just careful with the signs that they don't that you don't forget to distribute the negative sign. Now, multiplication, that was addition and subtraction. Multiplication of complex numbers is performed the same way as multiplications of polynomials. So we're going to use the distributive property. We're going to use the FOIL method if we have 2 binomials. When you are done, you have to do that. We cannot leave any power of I bigger than 1. So if you have an I squared, because they simplify, if you have an I squared, it's going to change into negative 1. Okay? Let's try with a basic distribution problem. So this turns into 12i minus 20i squared. Okay, now the I squared turns into a negative 1. Multiplication comes before addition and subtraction, so that's 12i plus 20. But always write complex numbers, always write them in standard form, which means the real part first and then the imaginary part second. Okay? Next, part B, we have 2 binomials. So let's FOIL them together. First, that is negative 14. Outside, that is negative 35i. Inside, negative times negative, that's a positive 6i. Tricky with the last one. Okay, let's take the last one a little slower. That's a positive 15i squared. Okay, I squared turns into negative 1, and so this turns into a negative 15. Okay, so we have negative 14 plus 30, or minus 35i plus 6i minus 15. Combine the real parts, combine the imaginary parts, negative 14, negative 15, negative 29. Negative 35 plus 6 is a minus 29 again with an I. Okay, let's try our 2 checkpoints. Okay, so find the products again. So this would be 14i, right, to distribute, and that would be a minus 63i squared. Again, I squared turns into negative 1, so that's 14i plus 63. Write it in standard form like that. Okay, Now let's do the I squared in one step. So we get 30 outside. That is a minus 35I. That is a plus 24I. And then 4 times 7, 4 times negative 7. So that's negative 28I squared, which turns into a positive 28 because the I squared turns into a negative 1, changes the sign. So 30 and 28, the real parts, give me 58. And negative 35 and 24 give me a negative 11I. Okay, so distribute, I squared changes to negative 1. Okay, let's talk a little bit about division. That was addition, subtraction, that was multiplication. Now we're going to do division. So division is not like we are going to be dividing. We're not going to be using long division or anything weird like that yet. But all we're going to do is simplify fractions, right? And this is kind of going to work like a radical does, right? We can't leave radicals in the denominator. So how do we clear them out? We multiplied by something that would make the bottom not a radical. And if it happened to be a binomial, we would multiply by the conjugate, okay? And that's what we're going to do here. It's possible to multiply imaginary numbers and obtain a real number. We do it when you multiply two conjugates together, two complex conjugates together. So look what happens when we multiply a plus bi and a minus bi. First, we get a squared, then minus abi plus abi, which cancel each other out. And then the last term is negative b squared I squared. I squared turns to negative 1, multiplies with the b squared to give me a positive b. So this expression, a squared plus b squared, will occur with no i's anytime you multiply two complex conjugates together. So for a number, a plus bi, the conjugate is always going to be a minus bi. And in both cases, whether it's a plus, then a minus, then a minus, then a plus, you're always going to get a squared plus b squared. As a shortcut, you can just jump right to that. Okay? And so complex conjugates can be used to divide complex numbers. The goal is to get a real number in the denominator. We don't want to leave a radical in the denominator. I is the square root of negative 1. Okay, so we don't want to leave that in the denominator. So the real number in the denominator, to get it, you would just multiply the denominator by the conjugate to turn the imaginary number into something that is real. Okay, let's see how it works. We're going to start with 7 plus 4i divided by 2 minus 5i. So this is really our division problem, okay? But the way we're just going to simplify it by multiplying the top and the bottom by the conjugate of the bottom. So that's 2 plus 5i on the top and the bottom, okay? Let's do the bottom first because it's a little bit easier. Remember that the i's go away and we get a squared plus b squared. So a is 2, so that's 2 squared plus b squared, the b, not bi, the b is 5, so that's 25. So my denominator is 29. All right, we're going to have to FOIL the top out here. So that's going to be a 14 plus 35i plus 8i. And then the last one is going to be 20i squared, which is a negative 20. Okay. 14 minus 20 turns me into negative 6. 35 and 8 is a positive 43i. Now, that is my expression. It can't be simplified, but we should express my answer in standard form, which is a plus bi separated. So we're just going to separate these fractions. So that's negative 6 over 29 plus 43 over 29i. Let's do our checkpoint. Ooh, cut off. Okay, so we have 5 plus 4i over 4 minus I, we're going to multiply the top and the bottom by the conjugate, which would be 4 plus I. The denominator turns into 16 plus the number in front of I is a 1. So that's going to be 17. The numerator, so we get a 20 plus 5I plus 16I. And then 4I times I is 4I squared, so that's minus 4. So that would be 16 plus 20, 1I. So my answer in standard form, 16 over 17 plus 21 over 17I. Great. Let's talk a little bit about how i's and square roots work a little bit, square roots of negative numbers. So think about this, that the square of 4i and the square of negative 4i are both negative 16. And you can see that right here, okay? Just like the square of like 4 squared and negative 4 squared are both equal to a positive 16, okay? So when we talk about the complex number system, everything has two square roots, the positive and the negative, the principal square root and the negative square root. Okay, so we call 4i, the positive one, the principal square root. Okay, so for any positive, just like we would with any other square roots, even if it wasn't imaginary. So for any positive real number b, the principal square root of the negative number is defined by the square root of negative b is equal to I times the positive square root of b, right? So if I wanted the negative root, I would put the negative in front, right? The symbol for square root means principal square root means positive on the outside, okay? But there can be an issue here. Let's look at this. So consider this multiplication problem right here. 5i times 2i. Well, from what we did before, that's 10i squared, which changes to negative 1, which gives me negative 10. Okay, but what if I wrote it in its square root form? 5i is the same thing as negative 25. 2i is the same thing as negative 4. Okay, but if we combine the radicals first, like it does in this incorrect example right there, if we combine the radicals first, we would get a positive 10. Right? Saying, okay, well, they're square roots. I can just put them both together. Negative times a negative gives me the positive 100, so I would get 10. However, that is incorrect because what you just used right here to combine these square roots was the product property. The product property only works for real numbers. The square root of negative 25 and the square root of negative 4 are not real numbers, so you cannot use the product property. So if you look at the bold sentence right there, when performing operations with square roots of negative numbers, begin by expressing all square roots in terms of I. That means if you are going to multiply these two things together, the first thing you do is take out the I and take out the I, and then you can combine them, and then you can do the other operations. The first thing you do always when you are simplifying or doing operations with negative square roots is to take out the I, put it in terms of I. Let's try that. So I can't combine, well, I couldn't combine those square roots anyway until I simplified them, but you can't even simplify them until you do the first step. Put it in terms of I. So this turns into I square root 18 minus I square root 8. Okay, well, what's the square root of 18? Well, that's 9 times 2. So that's 3I square root 2 minus square root of 8 is 4 times 2. So that's 2I square root 2. Hey, look at this. Same radicals. Like terms in the front. Now I can subtract them, and I just get I square root 2. But you couldn't do that until you simplified the expression first. For part B, remember that when you square a binomial, right, you get a middle term right? So hopefully everybody remembers that, okay? But the first thing you have to do before you even do anything is take out and make it in terms of I, okay? So then we get a squared, so that's 1, plus 2 times negative 1 times I radical 5. So that's minus 2I radical 5. The last one is tricky. It's b squared. So that's I squared radical 5 squared. Radical 5 squared is 5. I squared is negative 1. So that's a minus 5. So my answer becomes negative 4 minus 2I square root 5. And then for the last one right here, until we'll do some checkpoints after this. But the first step, the very first step before you do anything else is put the square root in terms of I. Then I can simplify it, right? It's 25 times 2. So that's negative 25 plus 5I square root 2 over 15. And then they all have a common factor of 5, so I can simplify this expression. And I want to write it as a two separate fractions anyway, so that turns into negative 5 over 3 plus I, well, let's make this nicer, square root 2 over 3. Now, you could put the I in the back, but because there's a radical here, it is usually better to default to putting it into the front of the fraction if you have a radical. Okay, even though we're putting it on the side of a fraction, so it makes it a little easier to tell that it's not part of the radical. Good habit is if you have a radical, put the I in the front. Okay, let's try the checkpoints. Okay, and of course, we're always going to write our result in standard form. All right, so first thing we have to do, I square root 27 plus I square root 48. Before you do anything else, we have to do that. So simplify that. That's 3I radical 3. And the square root of 48 is 4I radical 3. The 3 and the 4 add together to give me 7I square root 3. Okay. For the second one, the first step is negative 2 plus I square root 3 squared. Same as before. A squared is going to be 4 minus 4I square root 3. And that would be minus 3 on the back side. I squared, radical 3 squared to give me a minus 3. So that would be a 1 minus 4I square root 3. Last one, 14. First step, put it in terms of I over 2. And again, well, before we simplify, before we start to cancel anything, let's take the square root of 12, which is 2 square root 3 over 2. And now at least they don't leave me with a fraction anymore. So we just get negative 7 plus I square root 3. And definitely, if you have a radical not in a fraction, definitely leave the I in the front. All right, so let's finish up with quadratic equations with complex imaginary solutions. So we have seen that quadratic equations can be expressed in general form by setting it equal to 0, right? Ax squared plus bx plus c. And you can solve it using the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. And the part underneath the radical, that b squared minus 4ac, which is called the discriminant, and if that part is negative, the quadratic equations has no real solutions. However, it still has two solutions. They're just not real. They are imaginary solutions, and they're always going to be, because of this plus or minus right there, because of the way that this function actually works when we completed the square to solve for x in the quadratic equation to get the quadratic formula, they're always going to be complex conjugates. Let's see what happens. Okay, so to use the quadratic formula, right, I need to know a, which is 3, b, which is negative 2, and c, which is 4. And then I'm going to solve, right, negative b plus or minus square root of b squared minus 4ac all over 2a. And if you want, you can sing it to yourself, but I don't want to do it. All right, so negative 2 gives me a positive 2 plus or minus the square root of b squared is 4 minus 4 times a, which is 3, c, which is 4, all over 2 times a, which is 6. And we can clearly see that the discriminant is going to be negative. It's, right, it's 2 plus or minus square root of 4 minus 48 over 6. So it's going to give me a negative square root. So we get 2 plus or minus the square root of negative 44 over 6. And first thing to do is change it to an I. Okay, I'm going to go this way for a little bit so I don't have to keep going down. Square root of 44 is 2 plus or minus 2i square root 11 over 6. And we can cancel a 2, right? Factor out a 2 on the top and cancel it with the 6 to give me my answer of 1 plus or minus I radical 11 over 6, written in standard form would be 1/6 plus or minus in the front of the fraction 11 over 6. Okay. And those are my, whoops, sorry. I'm dividing everything by 2, so it is over 3, right? 2 over 6, 1 over 3. Okay. So that would give me my two solutions, right? The plus and the minus. Now let's try it again. So solve this quadratic formula. So A is 1, B is negative 2, C is positive 2. Just looking at it, right, I would first try to factor it, which you can't. And now I would use the quadratic formula. Negative B is going to be a positive 2 again, plus or minus 4 minus 4 times 1 times 2, all over 2 times A. 2 plus or minus the square root of 4 minus 8 is going to be, let's just do, right, just negative 4 over 2. And this is going to work out nicely. So that's 2 plus or minus 2. Well, first, right, let's do this step by step, right? You have to do that first still, right? I can do it all in one step. Yeah, it's going to be 2i. So 2 plus or minus 2i over 2, which makes my answer, right, 1 plus or minus I. Okay, we still, the first step, if we're simplifying a square root with a negative number in it, the first step is to take out that I. Okay, and that was section 2.1, complex numbers.